Alright, we're going to work the first solubility problem. This solubility has to do with a simple salt and pure water and then with common ions. So the salt we're going to look at is silver carbonate, which has the KSP of 8.1 times 10 to the minus 12. So I'm going to stack them. We have plenty of room to work on the left, so I'm going to stack them by using the same equation so that it's easier to see. So silver carbonate, solid, dissociates to form two silver 1 plus ions plus carbonate ion, both of which are aqueous. Okay, my KSP value is given, so we'll go ahead and put the KSP expression. It's going to be silver plus squared times carbonate 2 minus. So there's our expression, and the next one we need to do is the ICE table. So initial, change, and equilibrium. So initially we have 1, which is pure solid, 0 and 0. Then we're going to lose X amount. We're going to dissociate. Now because silver has a coefficient of 2, we're going to gain 2X, and we're going to gain X of carbonate. So at equilibrium, since we still have solid, we're at 1, 2X and X. So if we plug in our values, we're going to have 8.1 times 10 to the minus 12 is equal to 2X squared times X, which the most common mistake is to forget to square the 2, but if you square everything within the parentheses, that will be 4x cubed. So in order to solve for it, we're going to divide both sides by 4. So we have x cubed is equal to 2.025 times 10 to the minus 12th. In order to solve for x, we're going to take the cube root of both sides. Now remember, the other way to take the cube root is x cubed raised to the 1/3. Whoops, 1/3, not 1/2. Okay, so that's another way to do it if you can't find the cube root symbol on your calculator easily. So x then is equal to 1.2651 times 10 to the minus 4 molar. So that is our solubility in pure water. So that's the most we're going to get. Now for B and C, we're going to do common ions. One is the cation and one is the anion. And remember, all nitrates are soluble. And that's why they're often used as a common ion. And also all group 1, like sodium, potassium, etc. Our salts are soluble. So when we do B, what we're working with is the exact same thing, except we have a slight twist. The twist is, here is my ICE table. So initially we're going to start with the solid, but this time instead of having 0 silver, we're going to go ahead and have 0.002 molar. Okay, initially with the carbonate we're going to have 0. Notice I'm following down. I'm going to do that. It's a little time saver. So we're going to lose X. We're going to gain 2X plus X. But since we still have a solid, we're left with X. So it's 2X plus 0.002 and then X. So if we go back, our K expression is pretty much the same. 8.1 times 10 to the minus 12 is going to be equal to 2x plus 0.002 squared times x. Now, if we look at it, 0.002 is 3 decimal places. Our best case scenario is going to be this value. That's not a lot in comparison. So what we're going to do is make our math life a whole lot easier. What we're going to do is assume that 2x is much, much, much less than 0.002, so we can ignore it, eliminate it, whatever. So that means that 8.1 times 10 to the minus 12th is equal to, and when we eliminate it, we're going to pull it out, so we're going to have 0.002 squared times x. Now, we made our math a whole lot easier on this one. So if we look at it, if we square it, well, we end up with 4 times 10 to the minus 6 x is equal to 8.1 times 10 to the minus 12. That means if we do our math, our x will be equal to 2.025 times 10 to the minus 6 molar. So our solubility dropped, which is what we would expect. Now, because we made the assumption, we have to check it. If you don't, it is not valid. So what we do is we say that 2x over 0.002 times 100 needs to be less than 5%. So if we do the math, we get 2 times 2.025 times 10 to the minus 6th over 0.002 times 100, which comes out to be a whopping 0.2025%. Now, last time I checked, this is less than 5%, so it is valid. It's a valid assumption. Okay? So, if you'll notice, we lost solubility based upon the common ion. Okay, so we're going to do another one. This one now is going to involve the carbonate ion. So we're going to do an ICE table again. So it's still 1. The silver is still 0, but now for the carbonate, okay, I'm following it down from there, I have a value of 0.002. This is minus x plus 2x plus x, so it's still 1 here, 2x and 0.002 plus x. K-value expression is still the same, so we're going to set it up. So minus 12 is equal to 2x squared times 0.002 plus x. Now, because our amount is less to begin with, it checked before, it's probably going to check again. Let's make our math easier. So we're going to assume, in this case, that x is going to be much, much less than 0.002. If that's the case, so we can ignore. That means we end up with 8.1 times 10 to the minus 12th is equal to 2x squared times 0.002. Alright, at this point in time, we do our math and we end up with a whopping 0.008x squared. That means x squared is equal to 1.0125 times 10 to the minus 9th. You're going to take the square root of both sides, so x comes out equal to 3.18198 times 10 to the minus 5 molar. So, if you'll notice, we're much smaller than initially our pure, but got more solubility than our cation because it had doubled the effect. Now we still have to check it. So our check is going to be x over 0.002 times 100, which So when we substitute it in, it's 3.18198 times 10 to the minus fifth over 0.002 times 100, which comes out to be 1.591%. That's a check. We're less than 5, so we're good to go. This is how you work a solubility problem with common ions.